Hello everyone. My name is Dr.E.Purushotham, Professor of Physics, Department of Basic Sciences, School of Sciences and Humanities. Today, I am going to discuss about conservation of laws or conservation laws. So, conservation laws are three types mainly. So, what is the conservation of energy? First of all, energy can neither be created nor be destroyed. You try to see here. So, conservation laws in physics, the term conservation refers to something which does not change. What is this meaning? You try to understand that the variable in an equation which represents a conserved quantity is constant over the complete time. It has the same value both before and after an event. So the term conservation that represents the total quantity is constant over the time, or that value both before and after the event also same. So there are many conserved quantities in physics. They are often remarkably useful for making predictions in what would otherwise be very compiled situations. In mechanics, there are three fundamental quantities which are conserved. These are conservation of energy, conservation of linear momentum, and conservation of angular momentum. Coming to first one, conservation of energy. Energy can neither be created nor be destroyed. The total energy is always constant. The law of conservation of energy states that energy cannot be created or destroyed. However, you can see here, however, it can be converted from one form to another form or transferred from one object to another object. It is also defined as the total energy in the universe will never change. So, what are the examples? You try to see here. What are the examples? In hydroelectric power plants, water falls on the turbines from height. This in turn rotates the turbine and generates the electricity. That is the hydroelectric power plants. The potential energy of the water from some height, the water is falling or water falls on the turbine from height. Due to the height, it has the potential energy. The potential energy of water is converted into kinetic energy. The turbine is rotating. The rotating turbine has some velocity. So half mass into velocity square, half mv square gives the kinetic energy. So the total potential energy of the water is converted into the kinetic energy of the turbine, which is further converted into electrical energy, that is electric power. So coming to next one, fingers hitting piano keys transfer energy from player's hand to the keys. In a loudspeaker, electrical energy is converted into sound energy. In a microphone, the sound energy is converted into electrical energy. In a generator, the mechanical energy is converted into electrical energy. So conservation of energy, what is the example? That is freely falling body, freely falling body. Consider a body of mass m. Consider a body of mass m. For example, this is the object. It is at point A. It is freely falling from point A to coming to this. At point A, the initial velocity u is equal to 0. In between, another point I am taking, this is point B, this is point C, point C. So consider a body of mass m, which is freely falling from a height h. So I am taking this is from height h. So consider a body of mass m, which is freely falling from a height h. Let x be the, this is x. Let x be the, this is x. Let x be the downward distance traveling by the body in moving from point A to point B. In figure, A is the highest point and C is the point near the ground. So what about this height? H minus x. This is h minus x. Let us calculate the kinetic energy and the potential energy at various points in the path of the freely falling body. So first of all, I am taking number 1 at point A. At point A. So at point A, the initial velocity u is equal to 0. What about kinetic energy? Half m into u square. U is 0. So kinetic energy is 0. Height from the ground h. So what about potential energy? Potential energy is equal to mgh. Let this is, so total energy is equal to kinetic energy plus potential energy. So this is equal to kinetic energy is 0, potential energy is mgh. So total energy E1 at point A is equal to mgh. At point A, EA is equal to mgh. Let this is equation number 1. Equation number 1. So at point B also, second one, we need to calculate at point B. At point B. So velocity at point B, try to take, this is VB. Velocity at point C, this is VC. So at point B, kinetic energy is equal to half m VB square, half m VB square. Let this is equation Roman number 1. Initial velocity from point A to B. You try to see here point A to B. From point A to B, at point A, initial velocity u is equal to 0, final velocity is equal to VB, s is equal to the distance is x. So acceleration a is equal to plus g. So substitute all the values in v square minus u square is equal to 2as. So this is v square vb square minus 0, that is 2gx. 2gx. So substitute this VB square value. Now substituting VB square is equal to 2gx in equation 1. So kinetic energy is equal to half m VB square, that is 2gx. So 2 gets cancelled. That kinetic energy is equal to mgx. So coming to potential energy at point B, potential energy you take here. So potential energy m into mg into that height h minus x. This is the height from the ground. So potential energy is equal to mgh minus mgx. Total energy is equal to kinetic energy plus potential energy. So total energy at a point B, that is EB, is equal to kinetic energy mgx, potential energy mgh minus mgx. mgx gets cancelled. At a point B, EB is equal to mgh. Let this is equation number 2. Equation number 2. So at a point at a point C, at a point C, already velocity v is equal to vc. So kinetic energy is equal to half m vc square. Let this is Roman equation number 2. As the body is falling from a height h, so substitute v square minus u square is equal to 2as. This is vc square minus 0. This is 2gh. So now substitute, now substituting the vc square is equal to 2gh in equation 2, in equation 2. So we get kinetic energy is equal to half m into vc square, that is 2gh. 2 gets cancelled. Kinetic energy is equal to mgh. What about potential energy? Height 0, potential energy is equal to 0, but total energy is equal to kinetic energy plus potential energy. So total energy is equal to kinetic energy, that is mgh, potential energy 0. So total energy at point C is represented by EC, that is equal to mgh. This is equation number 3. Equation number 3. So here the equation 1 you try to see here. 1, this is 2. EA is equal to mgh, EB is equal to mgh, and EC is equal to mgh. mgh. From equations, from equations 1 comma 2 comma 3, it is clear that the total energy of a freely falling body is remaining constant at different points of its path. Hence, freely falling body obeys the law of conservation of energy. So, the sum of kinetic and potential energy, or principle of conservation of energy, may also be states the total energy in any system is always remains constant. So you try to understand here conservation of energy, freely falling body. Suppose conservative forces operate on a system of particle if final UF and initial UI be the final and initial potential energies of the system and W be the work done. Then the final potential energy minus initial potential energy is equal to negative of the work done, or work done is equal to change in kinetic energy, the final kinetic energy minus initial kinetic energy. By substituting equation 2 in 1, so left side, this is minus W, this is plus W. So we can write this is UF minus UI is equal to this minus of KF minus KI. So final potential energy plus final kinetic energy is equal to initial potential energy plus initial kinetic energy. The sum of the potential energy and kinetic energy is called as total energy. According to this conservation of energy, the energy can neither be created nor be destroyed. It can be transferred from one form to another form. Let us consider the case of a body of mass m. This is the m at a height h above the ground. If to position A, the kinetic energy of the body is zero because of this initial velocity u is equal to zero, while its potential energy is mgh because potential energy is equal to mg into that height. The sum of these two energies is mgh at a point A. EA is equal to mgh, equation number 1. Now, suppose that the body falls through a distance x, where the velocity of the body becomes v. Using the formula v square is equal to u square plus 2gh. V is equal to root of 2gx. In this case, the kinetic energy of the body is of mv square half m into 2gx. So this 2 gets cancelled, we get mgx. The potential energy of the body. So potential energy is equal to mg into that height h minus x. You can see here the height is h minus x. The potential energy of the body is equal to mg into h minus x. Hence total energy E is equal to mgx, this mg into minus x. Mg minus x gets cancelled, remaining at a point B, at a point B, EB, that is equation number 2, is equal to that is mgh. Suppose the body reaches to ground where its potential energy is zero. Here the kinetic energy of the body is mgh. So here this is EC is equal to mgh. This is equation 3. From equation 1 to 3, EA is equal to EB is equal to EC, that is equal to mgh. So the sum of potential and kinetic energy remains constant. Hence, the principle of conservation of energy may also be stated as the total energy in any system is always remains constant. The variation in energy is shown in this figure. You try to understand. It is obvious from figure that the total energy remains constant mgh. So applications of conservation of energy, applications you try to see. In a torch light, in a torch, the chemical energy of the batteries is converted into electrical energy. The chemical energy is converted into electrical energy, which is converted into light and heat energy. In hydroelectric, already we discussed power plants, the water falls on the turbine from a certain height. It rotates the turbines and generates the electricity. Hence, the potential energy of water is converted into the kinetic energy of the turbine, which is further converted into electrical energy. Here also, in loudspeaker, electrical energy is converted into sound energy. In microphone, the sound energy is converted into electrical energy. In generators, mechanical energy is converted into electrical energy. When the fuels are burnt, chemical energy is converted into heat and light energy. So, chemical energy from food is converted into thermal energy when it is broken down in the body and used to keep it warm. Conservation of linear momentum. Conservation of linear momentum. When the external force, so external force, F external force acting on a system or particle is zero, then the linear momentum of the particle remains constant. So try to see here linear momentum of the particle P is equal to mv, mass into velocity. According to Newton's second law, the external force F external is equal to ma. So this is equal to m into acceleration dv by dt. So this is equal to d m into v divided by dt. So this is equal to that is dp by dt. dp by dt. So f external is equal to dp by dt. F external is equal to dp by dt, or dp by dt is equal to F external. According to the definition, the external force acting on the body is equal to zero, then the linear momentum is constant. D by dt of constant is equal to zero when the external force acting on a system or any particle is zero, then the linear momentum p of the particle remains constant or conserved. So let us take a momentum p is equal to mv. External force F external is equal to mass into acceleration. M into acceleration, that is dv by dt, that is dp by dt. F external is equal to dp by dt when the external force acting on the body is equal to zero. That is dp by dt is equal to zero, then p is constant. That is conservation of linear momentum. Applications for conservation of linear momentum. So here you try to see the launching of rockets. The rocket fuel burns and pushes the exact gas in the downward direction. Because of this, the rocket gets pushes in an upward direction. The total momentum of the system, including the rocket and fuel, remains the same as before the rocket's repulsion. So, motorboat, it pushes the water backward and gets pushed forward so as to conserve the momentum. So, gun recoil, billiard, and pool also. When a bullet is fired, you try to see here. So, the launching of racket, you try to see clearly. The launching of racket, So the rocket fuel burns. So this is the fuel is burnt. The rocket fuel burns and pushes the exhaust gas in the downward direction. Because of this, the rocket gets pushes upward direction. The total momentum of the system, including the rocket and also fuel, remains the same as before the rocket's repulsion. So try to see the launching of rocket. Coming to second one, gun recoil. This is the gun recoil. You try to see when a bullet is fired, the gun experiences a backward force. Every action has an equal and opposite reaction according to Newton's third law of the motion. The combined momentum of the recoil, the gun and bullet is still zero. So this is the conservation of linear momentum. Conservation of angular momentum. When the external force, at the time of external force in linear momentum, we will use the external torque in angular momentum. When the external torque acting on a system or particle is zero, then the angular momentum of the particle or system remains constant or conserved. Explanation. According to Newton's second law, so external force F external is equal to dp by dt. So after calculation, we can take torque. The external torque is equal to position vector into dp by dt. Actually, the external torque is equal to r bar cross F external. That's why I am taking here. What is this? This is F external is equal to is dp by dt. So general, the external torque is equal to the position vector cross F bar, R bar cross F bar. So substituting here R bar cross F external or F bar. So that is dp by dt. That is equation number one. You try to understand here equation number one. But the torque, already I wrote here, R bar cross F external is equal to torque. This is equation number two. So R bar cross F bar is equal to external torque. That external torque R bar cross dp by dt. So angular momentum L bar is equal to position vector R bar cross linear momentum P bar. Differentiating the above equation both sides with respect to t, we get this is left side dl by dt, R bar as this crossed as this dp by dt plus p bar constant I am taking here into dr by dt. So dl by dt is equal to this r bar cross dp by dt, that is F external. You take here torque external, tau external. So into p bar cross dr by dt. So this dl by dt as this torque is also as this p bar linear momentum is also as this. The rate of change of position vector gives the velocity. At the place of dr by dt, we are taking here v. So dl by dt is equal to external torque plus so p m mv cross v. So take the bracket here. P cross V is equal to 0 because mod V sine 0. So sine 0 is equal to 0, that is 0. This is a dl by dt is equal to external torque plus 0. The external torque dl by dt is equal to 0 according to the definition. Simply we can discuss here. So we calculated this is external torque is equal to dl by dt. When the external torque acting on a system or particle is zero, then the angular momentum of the particle remains constant or conserved. The external torque T external is equal to dl by dt. L is the angular momentum. In the case of external torque applied to a particle be zero, we have the external torque is equal to zero, then dl by dt is equal to zero, L is constant. Thus, the angular momentum of the particle is conserved if and only if the external torque acting on a particle is zero. This is conservation of angular momentum. What are the applications of conservation of angular momentum? Rotation of the earth, we try to understand that is angular momentum. The rotation of the earth has not been affected by any external torque. So external torque is zero, which means the angular momentum of the earth is still conserved and the same as at the beginning. So spinning of an object, diving, ice scatters, spin faster, rotating machinery. These are the examples of conservation of angular momentum and also applications. So try to see here rotation of the earth. This is rotation of the earth. This is spinning an object. So rotation of earth. The rotation of the earth has not been affected by any external torque. The external torque acting on the earth is equal to zero, then the angular momentum is constant, which means the angular momentum of the earth is conserved and the same as the beginning. Spinning of an object, you see, spinning of an object, spinning an object, spinning an object, a plate or a ball, and a finger or a stick is yet another example of the application of the law of conservation of angular momentum in our daily life or real life. So, diving, you try to see, you clearly observed here, diving. Divers use angular momentum conservation to execute complex flips and twists during dives. They adjust their body position, you try to see, to control their rotational speed and achieve the desired number of flips and twists before the entering the water. So this is the diving application in conservation of angular momentum. Thank you so much. Thank you all.